Welcome to Brainbox. In present session, we are going to discuss about the extraction of high reactive metals. See, in the previous sessions, we clearly discussed about how to extract very less reactive metals like copper, silver, gold, platinum, mercury. And in a similar manner, in the next session, we even discussed about moderately reactive metals. See, what are these moderately reactive metals? The metals like zinc, iron, etc. Right? And now in the present session, we are going to discuss about highly reactive metals. Right? So either in the moderately reactive metals or in the case of less reactive metals, we have converted all the other ores into their oxide ores, and then we have treated them with the reducing agents. Right? So depending upon the metal, we choose the variety of reducing agents. Like in most of the cases, the best reducing agent what we have used is carbon or even the carbon monoxide also, right? But for the highly reactive metals, we cannot reduce the metals by using carbon or carbon monoxide as a reducing agent, because here these metals are even more reactive than carbon. So for the reduction of such metals, carbon or carbon monoxide cannot be used as reducing agent. So high reactive metals cannot be used or cannot be reduced by carbon or carbon monoxide. This is very simple. The reason is that metals are more reactive than carbon or carbon monoxide. If those metals are less reactive than carbon or carbon monoxide, then only we can use the carbon or carbon monoxide as a reducing agent. So now what is the solution for this problem? The simple solution for this problem is that we can reduce all such metals by electrolytic reduction, right? So electrolytic reduction is used to extract such metals. Which metals here? The metals which are more reactive, like sodium, potassium, calcium, magnesium. For all such metals, we cannot use any other reducing agent. So for such cases, what is the best method for the reduction means, for all such metals, electrolytic reduction is the best method. So for this, let us see how to extract sodium from its compound. Sodium mostly available as sodium chloride, right? So electrolytic reduction of NaCl. Okay, so here we have to reduce the NaCl and we need to obtain sodium metal, right? So how to get this? See, whenever we electrolyze, we know that sodium chloride is an ionic compound, right? So as the sodium chloride is an ionic compound, it is very clear when molten metal is electrolyzed, it dissociates. It dissociates how? It dissociates to give its cation. What is the cation of sodium chloride? It is Na+, and similarly, it will even give the Cl- ion. It dissociates into cation and anion. Right. Now, among this, cation being positive in charge move towards cathode. So why moving towards cathode? See, you know very well that the ions will always move to the respective electrodes which are opposite in charge. Cations positively charged, so they move towards cathode which is negatively charged, right? There they will abstract the electrons and will be reduced. So at cathode, sodium, which ions will travel towards cathode? Cathode is negatively charged, so the positive ions will travel towards cathode, moves towards cathode, and the main reaction which is occurring at cathode is reduction, and they are reduced. So reduction means it is very simple that gain of electrons. What is the cation here? Na plus ion. And Na plus ion gains exactly 1 electron and is reduced to sodium. And this sodium metal, which is reduced at cathode, is deposited at cathode. Okay. And similarly, we'll see the next one at anode. Okay, at anode. See, at anode, which ions comes towards anode? See, we know that anode is positively charged, right? So, as the anode is positively charged, the negatively charged ions move towards anode. So, which ions? Anions here. So, anions move towards anode, and at anode it is always oxidation occurs, hence oxidized, right? So what is the anion here? Cl minus, right? So Cl minus ion loses electron and forms Cl, but anyway Cl, chlorine, does never, it is a non-metal and it is a diatomic gas. So to show that it is Cl2 formed, I am taking 2 Cl minus ions here, so that Cl2 plus 2 electrons, right? So at anode, what is happening? Anions are moving towards anode. At anode, they undergo oxidation, means losing of electrons, and liberate the gas. So what is liberated here? Here, chlorine is liberate. Okay, so during electrolysis of sodium chloride, what are the products obtained? You see here, see, first thing, electrolysis of sodium chloride gives us that Na plus ions in the sense cations, similarly Cl minus ions in the sense anions, right? So sodium ions being positive in charge move towards cathode, and at cathode they will be undergoing reduction. Now after reduction, that sodium metal is deposited at cathode. Similarly, anions, in the sense the negatively charged ions being negative in charge, they travel towards the positive electrode in the sense anode, and at anode they undergo oxidation. So oxidation means what? Loss of electrons. So that, see, Cl minus will lose electron. But anyway, the compound of Cl minus Cl, chlorine, is that in elemental form it is diatomic, hence Cl2. So because of this reason, what I have taken is, I have taken 2 Cl minus ions which will release 2 electrons to give Cl2 gas. So chlorine gas is liberated at anode, right? So this is the way how you will extract the metal. So whatever may be the metal extracted, it is the common process what will go on. The metal will be always deposited at cathode, right? So where we can get the metal? During extraction of highly reactive metals, we can electrolyze their molten solutions. But after electrolysis of the molten solutions, the metal always can be deposited at cathode. So we can extract the metal from cathode, right? Have a look now.